Hello, and welcome to the AI Research Roundup. I'm Alex. It's May 10th, 2025. Today, we're looking at an ICLR conference paper, a theoretically principled sparse, connected, and rigid graph representation of molecules, published about 3.5 months ago. This paper tackles how AI models, specifically graph neural networks or GNNs, represent molecules. These graph neural networks need molecular graphs that are sparse, having few connections, connected, with all atoms linked, and rigid, ensuring a clear 3D structure. This paper introduces Spherical Convex Hull, or SCHull, a novel method that projects atoms onto a sphere and uses their spatial arrangement to build these improved graphs. Okay, so this first figure really highlights the problem Spherical Convex Hull is trying to solve. We see a protein molecule, and then two ways of representing it. One uses what's called a radial cutoff graph, a common method where you connect atoms if they're within a certain distance. This approach often results in graphs that are either too dense or disconnected. But the Spherical Convex Hull graph looks much cleaner. The plots then show that Spherical Convex Hull consistently produces graphs with a low edge-to-node ratio. That's the number of connections per atom, indicating good sparsity, and maintains a high percentage of connected graphs, ensuring all atoms are linked. Alright, so this table then clearly contrasts different graph construction methods. It looks at whether they achieve good sparsity, connectivity, and that crucial rigidity we talked about. You can see methods like the radial cutoff, or even k-nearest neighbors, which connects an atom to its k-closest neighbors, often fail on at least one of these. For instance, they might be sparse but not fully connected, or lack rigidity. But Spherical Convex Hull, it's the only one shown here that successfully achieves all three, which is a big deal for molecular modeling. Okay, so to see how Spherical Convex Hull actually achieves these properties, this next figure really walks us through the construction process. On the left, we see the original atoms, the blue points, which form what's called a point cloud, basically a set of 3D coordinates. These atom points are then projected onto a sphere around the molecule's center, becoming the orange points shown. Then, the middle panel illustrates the creation of a convex hull for these projected points. You can think of a convex hull as the tightest possible boundary enclosing a set of points. Finally, the right panel shows how the edges from this convex hull define the connections in the final graph for the original atoms. This clever projection and hull construction is what helps ensure the graph is both sparse and connected. Building on that construction method, this table then shows some really compelling results. It's looking at the performance of different graph neural network architectures, like DimeNet, SphereNet, and LeftNet. On the MD17 dataset, a benchmark for predicting atomic forces. The key metric is mean absolute error, or MAE, a measure of prediction error, so lower is better. And consistently, when Spherical Convex Hull is added, the mean absolute error drops across various molecules, like aspirin. The training time per epoch, one full pass through training data, only slightly increases, showing this improved accuracy doesn't come at a huge computational hit. So moving from atomic forces, this next table demonstrates Spherical Convex Hull's impact on classifying protein functions, like enzyme reactions and protein folds. The key metric here is accuracy, where higher percentages mean better performance. For several different graph neural network architectures, such as MACE, SCHull, and ProNet, incorporating Spherical Convex Hull consistently leads to improved accuracy on these challenging tasks. The average training time per epoch also shows these gains come without a significant computational burden, which is really promising. Building on these promising results with minimal computational burden, this next table shifts focus to another important area, predicting protein ligand binding affinity, which is basically how strongly a drug-like molecule, the ligand, might attach to a target protein. The table shows results on the LBA test dataset. We see metrics like root mean squared error, or RMSE, which measures the average difference between the model's predictions and the actual values, so a smaller number means more accurate predictions. And then we have correlation scores like Pearson and Spearman. These tell us how well the trend in our predictions matches the trend in the real data, so higher values are better. For models like GVPGNN and ProNet, adding Spherical Convex Hull consistently improves these scores. lowering root mean squared error and increasing correlations, all with minimal impact on training time. Okay, so to better understand how spherical convex hull captures all this crucial information, this figure illustrates a really neat distinction. On the left, you have a basic convex hull of a point cloud. It just outlines the outermost points. But on the right, the spherical convex hull graph with its solid lines goes further. It also connects interior points, like X7 and X8, to the structure. This ability to include internal geometry, not just the outer shell, is key to how it enriches the model's understanding and leads to those improved predictions we've discussed. Alright, so in essence, what we've seen is that this spherical convex hull method provides a really solid, theoretically backed way to represent molecules as graphs. These graphs are sparse, meaning they're not overly cluttered with connections. They're connected, ensuring all parts of the molecule are linked, and they're rigid, which helps define their 3D shape accurately. And crucially, adding spherical convex hull to various graph neural networks, those AI models built for understanding relationships, significantly improves their predictive power across many important molecular challenges. That's our roundup for today. Thanks for joining me, Alex, and I'll catch you next time.